Hi, and welcome to this lesson on correlation. So this is kind of the second part to our lesson on statistical tests. Previously, we've just looked at the t-test, and today we're going to look at Spearman's rank correlation coefficient. So our aim today is to understand different types of correlation and also to test their significance. So as a starter, I'd like you to write a sentence describing the relationships shown by these two graphs. Okay, graph on the left, got speed, someone's running speed on the bottom, pulse on the y-axis, and the graph on the right, we've got kilometers run per week, and then the person's weight on the y-axis. Okay, pause the video now, write two sentences. Okay, so the graph on the left, you could have something like, that doesn't have to be exactly the same, but something like, as the speed of a runner increases, so does their pulse, for example. And then if you wanted to go into more detail, if this was an exam sort of style answer and you were looking to get maximum marks, you could give some numbers. So you could say, for example, when someone is stationary, their pulse, the average pulse is around about 62 BPM, and when they're running at 15 kilometers per hour, then the average pulse is somewhere around just below 120. For example, you could also say it's a directly proportional relationship, or it appears to be so. For the graph on the right, the data is a bit more spread out. It's not as easy to draw the conclusions, but we can still see a line of best fit. So this might be as more kilometers, or as the number of kilometers run per week increases, a person's average weight decreases, or something like that. Now, you know, we don't have the data as neatly close to the line of best fit, but we can still see a correlation. So what is a correlation? I'm going to look at that in a second, but first of all, let's return to the syllabus. Okay, here's the syllabus. So we are looking at this area here, and yesterday we've already sort of kind of done this, and we've also done this. So today we're really focusing on this one right here. The Spearman's rank correlation coefficient to consider the relationship of data. So, correlation, if you want to define it, it's the degree to which two variables are related. There's various other definitions, but I like this one, it's pretty simple. And to investigate that, let's look at these graphs here. Now, the graphs haven't got labels on the x and y axis, but it could be anything really. So, what you can do is you can, whilst I'm talking, start looking at those graphs and sort of estimate what line of best fit would you put across those different bits of data. And would you say that those variables are correlated? How strongly would you say they're correlated? Okay, I'll just pause the video for a sec so you can have a little think. Okay, let's start with the top row. So the top row, I've drawn in here what would the approximate line of best fit would be on top of that data. So we can see that this graph here shows data that is perfectly positively correlated. That means all the data is in a perfect line like that, and that would have a perfect positive correlation of 1. Here the data is a little bit more spread out. We can still see a clear correlation, but we can use some maths to work out that the correlation here is not perfect. For example, if we just highlight this value here and then this value here, okay, so when we move along the x-axis from here to here and get to this value, the actual y value goes down, okay, so it seems to have gone the wrong way in those two, and there's other parts as well. So for example, you know, going from this value and then it goes down to this value, so it's not perfect, so it's 0.9. Low positive correlation here, we can see the data is a bit more sort of noisy, a bit more messy, 0.5. And this one, there is not really any correlation. How would you know where to draw your line of best fit? Would you draw it this way or that way? Well, really, you shouldn't draw a line of best fit because there is no correlation there. Okay, perhaps you see where this is going with the bottom examples. Here, we've got negative correlations. So we start with a low negative correlation to a high negative correlation and then a perfect negative correlation where all the data is in a neat line, and the values we'd give there would be from minus 0.5 to minus 1. So that is what correlation means. It's kind of the strength of the relationship between two variables. Now, it's not good enough just to know the number for the correlation. We also have to establish whether a correlation is statistically significant. That means, did it happen just randomly, kind of due to chance, or is it something that we can really sort of count on as a real link between two variables? So we're going to do a worked example in a minute. But first of all, we're going to talk about when do we do this sort of test. Well, we used this sort of flowchart yesterday, you may remember. And yesterday we were talking about using the t-test down here. And Spearman's rank correlation coefficient, there's some sort of overlap in the type of data we would use. So first of all, both the tests, Spearman's and t-test, are to do with looking at measurements. But Spearman's rank correlation coefficient is used when we're looking at associations between different measurements made from the sample taken. So, for example, we're looking to see if there's an association between a person's body mass and the number of kilometers they run per week, for example. That was one of the ones we looked at the beginning. So, let's do a worked example. So, the test tells us whether there is a statistically significant correlation between two measurements from the same sample when you have between normally 5 to 30 pairs of data. Remember, this would be a negative perfect correlation of -1, and this would be a positive perfect correlation of +1. So here's a little test for you. I want you just to estimate what correlation do you think these different graphs show. Just say a number out loud. You can write them down if you want to. You pause the video for a sec, but certainly say them out loud. What do you think? I'll reveal the answers in a few seconds. Okay. All right, well, here they are. +1, perfect correlation there on the left. 0, -1, that's about +0.6, and that's about -0.6. How did you do? Are you understanding these different correlation values? Okay, so now let's move on to our worked example. Here's a question. Does being good at maths make you better at biology? Potentially in this lesson, for sure. But let's see what we can conclude from some data. So here are some random student names that we've made up, from Anand to Jasmine. Some exam scores in maths and some exam scores in biology. So are they linked? Pause the video, have a quick look, and just see what you think, just based on looking at the data. Okay, maybe you've come to a conclusion, but any conclusion that you've made now is going to be very subjective. It's not going to be statistically backed with evidence, so how can we make it more quantifiable and more rigorous? We use the Spearman's rank correlation coefficient. So how do we do that? Well, the first thing that we need to do is we need to look at this formula here, okay? So Spearman's rank correlation coefficient, given the symbol R subscript S, is equal to this. So it's 1 minus, this is a big bracket here, 6 times the sum of the differences squared. I'm going to explain what this means, this differences here. It's the difference in the rank of the two measurements. And then over here, it's n, open bracket, n squared minus 1, close bracket, which is the number of, and n is the number of pairs in the sample. So to do this calculation, the first thing that we really have to work out is this. We have to work out the differences. And it's best to do that using a table, which we're going to do in a minute. So, also, this test is going to work based on a null hypothesis. Okay, so H0 is the null hypothesis. And in this case, our null hypothesis, which remember which we're kind of seeking to disprove, is that there is no statistically significant correlation or link between maths and biology scores. Now, if it turns out that our statistics disprove the null hypothesis, we'll then move on and say, okay, well, there is a significant correlation, and that's the hypothesis that we can then accept. So when we do this, we're going to calculate a value for RS, and again, we're going to then compare it to a critical value. And if R is bigger than that critical value, that means there is certainly, well, there's not certainly, but there is enough of a link that it is significant. And yeah, if we have a negative value for R, then it's a negative correlation. If we have a positive value for R, then it is a positive correlation. All right, so here is the table that we're going to do. So now the first step when we're doing this is to rank each set of data. So this is the same table that we had before, but I've just put in an extra column here so I can rank the data. What do I mean by rank? Well, I mean who got the best score in the maths exam. So if we look down here, Hector did extremely well. So Hector's rank would be 1 in this case. And then if we scan down and look at the second best score, that would be Gemma. So that would be 2. So there's the data there. Oh, I've gone from highest to lowest. But in this example here, which I've previously typed out, it looks like I've gone from lowest to highest. It doesn't actually matter. As long as you're consistent and use the same sort of scheme over here. So I'll just get rid of those 2 there. Now, on the right-hand side, there's a little bit of a problem because 2 people have got the same score. So how do we handle this problem? Well, we kind of do our ranking as normal. So in this case, again, I'm starting with the lowest value. That's Bernard here. Bernard did not do so well on both exams. And when we get to the problem, so once we've gone 1, 2, 3, 4, 5, 6, 7, now we get to the problem. Now, what should we do? Should we put one person as 8 and one person as 9? That wouldn't really be fair. What we do is we do this. Okay, we use a average rank. So because it was 8 and 9, both people take the rank of 8.5. Just, you know, as an example, if we had 3 people with the same, so ranks 8, 9, and 10, like that, then we would average all 3, which would give us 9. Okay, so that's what we do, and then we continue ranking 10 for Hector, who got the highest score for both exams. Okay, so now we've got the ranks for maths and the ranks for biology. We need to work out the differences in those ranks is the next step. So here's the table again. Now the difference here is going to be, I'm going to use maths minus biology. It wouldn't make a difference. You could do biology minus maths. Doesn't matter which way round you calculate the differences. So 3 minus 7 is minus 4. But it doesn't really matter which way round you do that. You could just write 4, because when you square it, whether you have minus 4 or 4, they're both going to square to 16. Okay, and here's the data that I have completed. There it is. And then you tally up, so you sum all these differences squared over here to get the total value, the sum of the differences squared. And that, in this case, is 68.5 down here. Okay, so now we're pretty much ready to do this calculation. Here's the formula again. So it's 1 minus 6 times the sum of the differences squared over n cubed minus n. I just simplified this. In the previous version, we had, I think, n squared minus 1, which you could see if you can expand it to that. Okay, so now remember that we calculated the sum of the differences squared is 68.5, and there were 10 pupils here. 10 pupils, so that's n, number of pairs. So now let's do some maths. So if we plug that in, 6 times 68.5, and on the bottom we have 10 cubed minus 10, so it's 1 minus 6 times 68.5 divided by 990. So 1 minus 411 over 990. And if we do that, we get 1 minus 0.415, which equals to 0.585. There is our number. So that tells us the correlation. But is it significant? What we know really from that is that the sort of shape of the plots, if we kind of plotted, let's say, math score against biology score, for example, like that, we're probably going to get some data that's looking a little bit upward sloping, but it's quite noisy, isn't it? We don't really, there is definitely a link there, some sort of overall correlation, but we don't know if it is significant. Maybe it was just down to random chance that this occurred. Okay, we know there's a positive correlation roughly, but is it significant? That's the next step. So, is it significant? Now we need to look up the value and compare it to a critical value in a statistics table. So in this type of statistics table, we don't need degrees of freedom. We're just looking for the number of pairs, okay? The number of students. We had, in this case, 10 students here. So we're looking at this row. And this is our critical value here, 0.65. So look, here, our value, even though it implies a bit of a correlation, it's lower than the critical value. So what does this mean? Do we keep the null hypothesis or do we reject the null hypothesis? What do you think? Say it out loud. Okay. Well, in this case, we must accept the null hypothesis. There isn't a statistically significant link between those two things. So, therefore, math score does not statistically significantly affect your biology score. Okay? So, good news if you thought that you didn't like maths for some reason, I don't know why, maths is wonderful, it's not going to affect your biology score as long as you get this key understanding. So, let's now pass it over to you, and I'm going to get you to do 2 pieces of work to kind of cement your understanding of this. The first one I'm going to give to you on this video. I'm going to pause to you at certain points, and I want you to complete it and then kind of mark it as you go. And then I'm going to give you a second sheet, which you're going to do on your own. Okay? So, here we go. Mad Jeff's Chaotic Firework Factory. It's quite a noisy place. And people on the street on Acacia Avenue living next to Mad Jeff's Chaotic Firework Factory are a bit stressed out because there's a lot of explosions going on. So, but is the stress level closer when people are closer to the firework factory? Do the people that live in this house over here, are they more stressed than the people that live on this house? And is there a statistically significant relationship on that street? So we can do this, well, we might do this biologically by measuring cortisol levels. That's a stress hormone, and actually it has been shown to be increased by noise, but is that happening in this street? So the more stressed an individual is, the higher their blood cortisol levels will be. So what we can do is we can look at the address of people. So the factory is at number 2, Acacia Road, was it? Acacia Avenue, number 2. And then we have the addresses going down here. So people who live further away from the factory, their address is a bigger number. And then we can look at the blood cortisol levels as well. So remember, to start with, we must come up with a null hypothesis. There is no significantly significant correlation between proximity or closeness to the fireworks factory and blood cortisol levels. All right, here's a table. Now, I've given this to you on Teams for you to fill out. What I'd like you to do is to pause this video, work through ranking all the addresses and ranking all the cortisol levels, working out the differences and the differences squared. Remember what to do if 2 people live at the same address. Can you remember how to do that? You can go back in the video if you can't. And then once you've calculated the whole thing, once you've calculated the value for R, then you can come back, okay? And then we'll look at the significance of that compared to the critical value together in a minute, okay? So pause the video, work through all this, and then you'll see how you do, okay? Go ahead. Okay, so we're going to go through it now. So by now you should have finished all of this table and worked out the value for RS using the Spearman's rank correlation coefficient formula. So if you haven't done that, pause again and go now. Okay, if you have, let's have a look. So first of all, the ranks, the address ranks. Now see what I've done here? Just highlight this here. This was a sort of average rank, isn't it, of between 4 and 5. We used 4.5. And then here again, we've got an average rank of 7 and 8. This one here, this is an average rank of 3. This is a 9, 10, and 11, which kind of has an average of 10. So just be aware of that. And then the cortisol ranks we've got there. Differences squared. Did you get those right? And that is the final value for D squared. I'll just leave it there for a second so you can check to see if you agree with me. If it's just a tiny bit out, then it might be a decimal place issue when you're working on your calculator, but hopefully you got pretty close to that number, 513. So that's not the R value because we still need to work that out. So the R value, did you spot the number of pairs in this case was 12? So the R value should have worked it out to be equal to minus 0.794. Now, hopefully when you got that number, you didn't panic and say, I've got a negative number, what's going on? Because remember, that negative number means there is a suggested negative correlation. We don't know yet if it's significant, but it's a fairly strong correlation that is negative, basically saying it looks like, from a brief glance at this number, that people are less stressed the further they live away from the factory, which makes sense. Now, how about the significance of this? So, for n equals 12, I'm just going to give you the critical value. It's 0.587. And our value was 0.794. So what do? Do we take the null hypothesis, or do we have to accept a different hypothesis? Pause the video, say it out loud. Right, yeah. So in this case, we reject the null hypothesis. There is definitely some significance there. There is a statistically significant correlation between proximity to the fireworks factory and blood cortisol levels. Okay? And because it's negative, it's a negative correlation. So basically, the further away you live, the less stressed you are. So that's the end of the work that I want you to do in this video. I'm setting you one further sheet, which I'd also like you to complete off the back of this video. And let's just check that we've kind of covered the syllabus, what we need to. Oops, sorry. So we've had an opportunity the other day to use standard deviation, to do t-tests, and now we've done the Spearman's rank correlation coefficient. So we've done all these things, all of these things over the last 2 lessons. Okay, thanks very much, and I will post the answers to that second sheet at the beginning of next lesson. Bye-bye.